So what actually is open window mapping? So open window mapping involves high density mapping of both atrial and ventricular side of the annulus. And the point of this is to determine and identify where exactly is the annulus and where is the gap in the annulus that represents an accessory pathway. And so this form of mapping is primarily performed to narrow down the area of interest. So you find that gap in the mitral annulus or tricuspid annulus and say, okay, this looks like where we have conduction through the annulus, so this must be where the accessory pathway is. And then you can start looking at the individual data points and look at the individual signals and see if you have those positive predictors of success. You know, your AV or VA fusion with your accessory pathway potentially, and an early atrial or ventricular electrogram compared to a stable reference. And so if we have an accessory pathway in the left posterolateral position on the left atrium, so here we can see an accessory pathway here, and we're performing RV pacing. So we're performing retrograde mapping of this accessory pathway. And so during RV pacing, we'll have conduction which will occur from the RV, and it will travel through the accessory pathway, and then it will depolarize the rest of the atrium like this. And so of course no conduction will cross the actual mitral annulus except through that accessory pathway region, because the mitral annulus is made up of fibrous electrically inert tissue, so it represents a barrier of conduction. So if we pace from the RV and we have conduction going through the accessory pathway and like this, and then we take a data point here. So we place a catheter in this location, and we take, how long does it take from the pacing spike to the EGM that we see here. And in open window mapping, we are not really concerned whether it was a ventricular EGM or an atrial EGM. All we're looking at is the timing of the EGM directly beneath the catheter. And so it takes, and this is obviously going to be a ventricular EGM because we're on the ventricular side of the annulus here. It'll be 80 milliseconds from the pacing spike, so we'll have a pacing spike, to our EGM here in location 1. So I'll put L1, and it's 80 milliseconds between that EGM. And if we move our catheter just a few millimeters away, so let's say we put our catheter here. Let me do this in a different color so that we can actually see it. Let me do this in red. So if we move our catheter here, just on the atrial side of the annulus, so just a few millimeters away, and then we measure the timing. So how long does it take to go from our pacing spike to the EGM that we see here? Now we're going to see an atrial EGM here because we're on the atrial side of the annulus. And there's going to be a big difference in timing from here to here because you don't have continuous conduction here. Conduction has to go all the way from here to the pathway, to the atrium, and then to this catheter. And so you have to account for this whole time all along here. And so there's going to be a big difference in timing. So it might take, for example, 180 milliseconds, and I'm just making up a number here, but it might take 180 milliseconds. Even though there's just a few millimeters of difference anatomically, the electrical timing is very different. And what this indicates, or what we can infer from this, is that there is not continuous wavefront of conduction between this catheter location and this catheter location. So we don't know where the annulus is exactly before we do a map like this, but what we can say is these catheter locations are very close together, and there's very marked difference in the timing of the electrograms. And so what we can infer is that there's not a continuous wavefront of conduction between here and here, because it's inconceivable that in a normal heart it's taking 100 milliseconds to travel from this location to this location. And so what we infer from this is that there is a discontinuity in our wavefront conduction time, and so that there's an electrically inert barrier between this catheter location and this catheter location, whether that be scar. But in this population with relatively normal hearts, it's unlikely to be scar. It's going to be more likely that this represents the mitral annulus, so a fibrous ring of electrically inert tissue between this catheter location and this catheter location. And so we can take points all along the mitral annulus, and we can define the mitral annulus in this way. We can move our catheter here, and then we can move it up here, then we can take it here, then we can move it up here. And some 3D mapping systems will mark an area of wavefront discontinuity with a white line. So if there's a big difference between two adjacent timing points, it will go, oh, there's wavefront discontinuity here, and so it will put a white line down, and that white line roughly represents a line of block, and that helps us define where is this fibrous electrically inert mitral annulus. And so what would happen if we put our catheter closer to the accessory pathway? If we looked at the EGM on either side of the accessory pathway, well, if we have our catheter and we place our catheter on this side of the accessory pathway, it's going to take a certain time for our RV pacing to reach that catheter, and we'll say that time is going to be from the pacing spike to the EGM, which is obviously going to be a VEGM. It's going to take 80 milliseconds, like we said earlier. So then if we put our catheter in this location on the atrial side of the mitral annulus, what will the timing difference be in location number 2? Well, it's not going to be a huge difference because we just have to travel to the catheter a few millimeters, and we have continuous conduction through that accessory pathway to the other side of the annulus. So it's only going to take, let's say, 90 milliseconds for the location 2 on the atrial side of the mitral annulus, and this will be an atrial signal. And so this tells us that there's continuous conduction at this point. And so there's no electrically inert barrier which is sitting between this location here. And this is unique to the location of the accessory pathway along the annulus. At no other point along the mitral annulus will you have continuous conduction occur. And so this is what open window mapping is. It's looking at the timing of thousands of EGMs on the ventricular side and the atrial side of the annulus. And this helps us define where exactly is that annulus and where exactly is there continuous conduction through the annulus, because that location of continuous conduction marks the location of the accessory pathway. And then we can start to look for our VA fusion at that point, and that can tailor our blood ablation strategy.